Prepared, so I just got here today as reference from. Um, so maybe I'll just discuss some. We will talk about the extension basically to like L2. We defined it for simple processes. Now we'd like to see the extension for L2 continuous martingales, and we will see how it's done, and maybe discuss some fundamental lemmas, and maybe I can share some insight about seed based formula or something like that. So okay. Uh, so recall from last class, we defined stochastic integrals for simple functions. So what are simple functions? Simple functions are can be expressed like this. So j equals to summation from j equals to 1 to n of phi j minus 1 of omega indicator sj sj minus 1 sj and this. And so it can be a bit tautologically, it can be rewritten as like f of sj minus 1 omega indicator sj minus 1 sj of t. And we saw that the integral f times uh, f dbt f of t. So I will just omit the omega um, from 0 to t is was written in this form that we have summation of sorry j equals to 1 to n f of s j minus 1, and we had d dsj minus dsj minus 1. So I have changed some notation from last class. So B stands for Brownian motion. So I'll just focus on Brownian motion for a while. But this holds true for martingales for general M continuous L2 continuous martingales. Um, and we saw some properties like so this map if maps to this integral of 0 to t of f d dt, f of t d dt. This is linear, and we saw the quadratic variation of this integral. So this integral is also a L2 martingale. Um, this quadratic variation of this f of t dt was given by 0 to t fs squared ds. So this was the Ito's isometry from last class, and so basically we also had that the L2 norm of this martingale, the L2 norm of this martingale of the
Aryadeep, one small question. So when you say isometry, it's usually a distance preserving map, right? Or
yeah. So basically the isometry is from these. So okay, I'll just define the norm next. So I'll explain why there is the term isometry. So I'll define the norm for the general continuous function, and then I'll just explain why it's called isometry.
Okay.
But this is for just simple functions, and So we saw some similar results. So now we would like to extend this to maps to functions which belong to this space L2 of lambda t product with probability. So lambda t is just the Lebesgue measure on this interval 0. So one thing to note is that most of the things that I'll be saying will be valid for this capital T equals to infinity as well, with some small modifications. But for now, let us just stick to the 0 for capital T finite, so that we get a understanding first. So what we'll do is we'll endow the space of all. So let M2CT be the space of all square integrable uh, continuous martingales, and will endow this space with a norm. So this norm for some martingale m will be given by this expression. The expectation of supremum of S to P 0 from S belonging from 0 to P of ms squared and whole raised to the power half. So this will endow this space of square integrable martingales with this norm. And some things to note is that number one, or just directly, so Doomb's maximal inequality gives us Doomb's maximal inequality gives us that expectation mt uh, mt squared, this is lesser than equal to expectation of supremum of plus 2p of ms squared. This is just basic. This one has nothing to do with do. This is just basic observation, and this is the step of do. So 4 times supremum of s lesser than equal to p of expectation of ms squared, and this is actually equal to by another application of Doomb's inequality, maximal inequality, that this is equal to 4 times expectation of mt square. So we have a both side bound for this norm. So if this is the norm, so can everyone see the cursor, this mouse cursor?
Yes, yes.
Okay.
So the last equality is
so this will be this will always be greater than equal to this one,
right.
and for the other direction we have due to this is the full statement of Doomb's, like we have
Okay, so
MP.
probably
Okay, I'll just write the statement of Doomb's then.
okay. Yeah, I mean, but okay, this whole inequality and the last equality is just an application of Doomb's maximal inequality.
Yeah, it's just direct. I mean the formula itself, just
Okay,
the
sure.
expression.
Okay.
Uh, But so in case of Dooms, we usually use the probability notice, the inequality for bounding the probability. But this is just a second one, so it's available on Wikipedia. This formula. Uh, so it's just applying that to applying Holder's inequality to that probability form. We'll get this formula. It's nothing to separate. But in
Okay.
the Wikipedia, even
The
Thanks.
it's
left
also.
one is trivial, right?
Yeah. That one is just basic.
Is the upper
M
bound.
T is lesser than. Yeah. M capital T is lesser than supremum. Um, so the thing to note is that we are basically able to control this entire norm, this supremum, by just the last point. So that is the main intuition. So we need only focus on this last in the last index, so capital T, in order to get in order to know everything about the topology and convergence and all that stuff. So here's a lemma. So the space M2CT as we define with the above norm is closed. closed as closed as a subspace of all L2 integrable uh, processes, you can say. Or so by closed, I basically mean that if we have a Cauchy sequence with this norm, um, we if we have a Cauchy sequence with this norm, then and it converges to some martingale, then the limiting martingale will also be discontinuous and it will also be L2 integrable. So L2 integrability is just follows by Fatou's lemma. That is just usual L2 closure. But this continuity, this I'll just prove why the limiting one will also be continuous. So first, um,
So this the limiting is also martingale is just this L2 convergence of martingales, is it?
yeah, L2 convergence of martingales of the martingales, yes, processes
Right. Okay.
from 0 to 2. Um, so just give me a moment. Just in this direction. Oh, yeah. So let Mn be a sequence of these martingales which are in this space M P to C such that we have Mn minus M, this L2 norm, or this M norm, M2 norm, this tends to 0, where we don't a priori know whether M belongs to this space or not. We have to show that. So basically now, since this we can control this norm uh, by the endpoints. We know everything about the convergence by using the endpoint NP. So since this is uh, so since we have that okay, I don't know how to write this. So I mean, so since we have that MT, this one converges in L2. Since this convergence of in this norm tells us about this norm and vice versa, we have convergence of in L2 sense of this is just L2 convergence, and L2 convergence gives us a subsequence in which almost sure convergence takes place. And so if we have so we can find a sequence, so mnk, such that we have this mnk such that we have, so here we were taking expectation of the supremum of s0 from s from 0 to t of ms square. So if we have convergence almost surely, means we can drop this expectation, and we can now say that this limit of k tending to infinity of mn sorry, this is just supremum of s to t, s0 from s lesser than equal to t of mn k of s omega minus m of s omega, this is 0. This we can say because we have almost sure convergence of this random of this sequence of random variables of c0 t valued random variables. We have almost sure convergence. So, and this is just convergence of the L infinity norm, right? This is just mnk of s omega minus, and this is almost sure. M s omega infinity, it equals to 0. So we know that now we can use the completeness of L in C0 T space with the L infinity norm, and this is complete, and hence we have that since this M is a limit of um, continuous functions, we have almost surely that this M of S is also S maps to M of S will also be a continuous function. And since we have that, so note that we have Mn of S in this convergence. Mn of S converges in L2 to M of S, and this holds for all S lesser than T. So we can now, for any f belonging to this sigma algebra fs, we have integral of f ms dp equals to the limit of n tending to infinity of integral of f mns dp. Right, this is just L2 convergence, and this equals limit of n tending to infinity of integral over f of mn of t dp. This is the martingale property of mn. And this is again, so since we have L2 convergence for all s lesser than equal to t, this also we have also L2 convergence of mn t. So this again equals integral of over f of m of t. So this proves that m is a martingale. So this basically proves that this space M2C T, this is closed under the this norm that I defined, this one. And since this norm is equivalent with this L2 norm of the same points, we can also say that it is closed under this L2 norm of n points. And that is in very trivial, that is closer to the L2 normal endpoint, but this is okay. Uh, so now, so like we saw in measure theory, like we used to do it first for simple function and then we go to like L1 function. So we can we can see that this space of these simple functions, like we saw last day, this will be dense, uh, are dense in um, this space M2CT, right? I mean, for any um, sorry, it's one second. What did I want to say? Um, yeah, sorry. This is not necessarily. So let this space ET denotes the linear span, denotes the span of all simple functions. And we take the closure of the space under the norm um, MT2, like we said. So, and we'll define the uh, stochastic integral for all functions. This and since so okay, so since this norm is compatible with this norm, um, L2 of lambda t times product, like we saw, uh, will define this stochastic integral of all f belongs to this et closure by uh, integral of f dbt, f of t dbt from 0 to t will be, this is a definition, integral of 0 to t, the limit n tends to infinity in the L2. Uh, I did not prepare the notations properly. So this L2 of lambda t is limit under this norm, limit of this fn or db, where fn is a sequence in this space et such that fn minus f this difference of the L2 norm of this difference goes to 0. So this will be our stochastic integral for this closure. And I'll come to what this closure actually is. It's actually very large, this closure. And there's something to do with the progressive measurable functions. So I'll come to that point later, but for now on. Um, so this Fn, so firstly, why is this definition unique? So
Argadeep, for
yeah,
Brownian integration with respect to Brownian motion, you can can't you actually do it for all adapted processes?
yeah, we can. So
right?
I'm just focusing on Brownian for now,
Okay. No,
so
but
that
yeah,
it's
I
easier.
just wanted to get this verified that for as long as the martingale, the quadratic variation of the martingale is absolutely continuous with respect to Lebesgue measure, you can
Yeah, yeah,
define
yeah,
it for adapted processes. But
yeah, yes,
if not, you have some smaller class probably. But yeah,
yes, yes, yes,
okay.
yes, yes. Um, so yeah, so why is this definition unique by the US? So if Fn um, and also why is this defined in the first place? So how do we know the why is it well defined anyways? So if Fn be a sequence which satisfies this property, then we have that this Fn integral of 0 to t Fn of dbt Fn t dbt minus integral of 0 to t Fm t dbt. This L2, okay, note that this is L2p, because these things are no longer dependent on uh, the time anymore. Uh, so this is equal to expectation of 0t of Fn of s comma dot minus Fm of s comma dot square ds. So this we proved last time, right? So we have that the we proved it for general martingales, that this in this case we just have d for the increasing process, but for Brownian motion this is the quadratic variation is just t. We just have this integral of square ds or dt, whatever. Um, and this is just um, Fn minus Fm L2 of lambda t product to t, and this tends to 0 as n and tends to. So this proves that if we have a Cauchy sequence in this norm L2 of lambda t comma p, then we have that this sequence Fn dbt, this will also be a Cauchy sequence. And so this makes sure that this thing is defined at least. So this quantity will be Cauchy as long as this Fn is a Cauchy sequence in this norm L2 of lambda t. Um, so and so here's a set of results which holds for this integral. So firstly, this map f maps to integral of 0 to f dt is a linear map from L2T. This script L2T is just the space of um, this. I was using L2 of lambda t roughly. So from this space L2 lambda t plus p to this NT Number two, so I'll come to the proofs later. Um, we have integral of 0 to p f of t ddt
So is
minus,
this L2 of lambda t cross p, is that the progressively measurable?
yeah,
That's the space of progressively
basically, yeah.
measurable processes, right?
Yes. So
Uh,
progressive. So we can no. This case of all L2 processes. We can prove that the closure under the norm, under closure of this ET under this norm is the space of all progressively measurable functions which are L2 uh, of
okay, so
lambda.
progressively measurable L2 functions basically.
Yes.
Okay.
So
Uh, I see. So,
uh, yeah.
but okay, but usually, like I mean, you have seen more stochastic calculus probably than me. So usually, so these most of these nice looking processes are all um, progressively measurable.
Yeah. Usually, yeah.
Okay. Okay.
Because we want to have that by, so we want to have ft should be measurable with respect to this interval like 0 t, right? Or else sigma algebra of 0 comma t. So that
Right.
is
Right.
usually all. I mean, most things will be progressively measurable.
Okay. But yeah, as long as you are doing it for DBT, probably even adapted would work.
Yeah,
So I
probably.
don't have to. So just by looking at f of t, if I see if I understand that it is adapted, then I don't have to worry about it being progressively measurable, right?
Yeah.
Okay.
As long as it's adapted and this norm is finite, this L2 of lambda
Right.
t
Right. Yeah.
cross.
Yeah. Sure.
Yeah.
Right.
In that case, uh, we can define this integral without any hesitation.
But checking that that norm is finite, is that a um, okay? Probably it depends on example to example. Yeah, you can.
No, I mean, see, for example, if this omega were to vanish, so if f was not dependent on omega, I mean, if it was a deterministic function, for example, let's say
Right.
sine t or something,
Right.
then we just have 0 to t of like sine square dt, right? Sine
Right.
square s ds, right?
Yes.
And even if we have dependence on omega, uh, so most of
So
those
yeah, if you are
functions,
saying all deterministic functions, if it is integrable on 0 to t, or
then
rather,
it's defined.
yeah.
Yeah,
So any L2 of 0 to t is uh, it belongs to this L2 of lambda t cross p, right?
yeah.
I see.
So for example, all deterministic functions which are L2 in nature,
Right.
we
Right.
have we have integrals of them. And even
Okay.
if omega comes, even then it's a matter of like expectation, right? Expectation
Uh,
of expectation of the square of the integral of 0 to t squared of for fixed omegas.
so for example, if I take f of t is itself my bt squared, uh, or
Bt squared, yeah, it's okay.
then
So you can do it one by one. So we can bring this integral. So I'll just show. So for
yeah.
example, we are talking about 0 to t of bt squared dbt,
Whether
right?
this, yeah, whether this is a so yeah, I want to ask whether this bt squared uh,
Yes.
actually belong or right, bt square
So
belongs to L square, this thing, yeah.
we can write it like this, right? We can write it like bt squared dt.
uh,
I
okay.
just by Fubini, I mean, I just brought the expectation inside.
Right.
and this is just a normal variable bt squared
No.
for each fixed t.
No, I meant. So what was? So you had to check whether integral of bt squared 0 to t d.
So we want to check whether bt dt of omega, this L2 of lambda t cross p is finite or not.
Right. Yes.
Right. So this by definition is expectation of 0 to t of bt, or we had bt squared, so this will be bt4 actually. So bt squared whole squared dt and the whole expectation. Right. This is this L2 norm squared. We are taking the root of this.
No,
but
should I see. Right.
okay.
Yeah.
So this is just so what we can do is bring the this integral outside this
No.
real.
This expectation, it's actually integral of omega bt square of omega, right? Then dp would be that.
Okay, I'll write the whole term.
Uh,
So we can write it integral over omega integral over t of bt of omega bt squared of omega whole squared dt dp.
right.
Is
So
that okay?
the inner, yeah. So the inner thing is actually expectation of this thing.
Yeah, inner thing is just expectation of dt to the power 4.
Right.
And this is equal to 3 3t squared, is it? Normal variable, what is it? I think so, right? Fourth moment.
Yeah, right.
Yeah, and then 0 to t dt.
Okay, so this is finite. I see. Okay.
So this is fine.
Yeah, right. So okay, so the integral of this thing is actually different. Okay, thanks.
Yeah. So yeah. So I'll even show you. So if there is time today, I'll even show you how to just give a explicit formula even for this integral. It is
Right, but that would be by Ito's formula, right?
That will be the Ito's formula. Yes.
Right.
So
But
I'll just give the
no.
I'll just give the heuristics, just the heuristics without any.
Okay. I don't know if it's a right use of time, but is it easy to see like approximating it by simple functions and so on, like the right, at least for some nice functions of b, whether what would be the actual simple
Yeah.
processor?
Yes.
Okay.
Okay. I can even show that if not Ito's formula. So um, instead of bt squared, I'll just show
No, I
this
mean
one.
before other that you were stating some properties of
Yeah. I'll finish the properties first.
Right. So
I don't know whether undo works, this control Z works or not. So not taking the risk pressing control Z.
you're working on your laptop, or you have joined through your laptop, and
Laptop.
so the laptop itself is touchscreen.
No. It's Windows, basic Windows.
Right, but okay, you have also joined a iPad to that, or
No, I'll Wacom that. Wacom.
I see.
Writing.
Tablet. Writing. Okay.
Yeah. So, so second property is that this integral f of t dvt minus. So this is a so this one is a martingale. So if, if we take the square minus this 0 to t of this of this squared dt. So since this is a martingale, this is a martingale, and
The
this is
second
its
term,
quadratic.
second term is its quadratic. So you
Quadratic.
should get a increasing process or something, right?
Yes, this is the increasing process. And it's easy to see, right? It's increasing, it's big, right?
Right.
And so this minus this increasing process. I mean, this is a submartingale. This the inner thing is a martingale, and this squared is a submartingale. So submartingale minus the quadratic variation, this will be a martingale. This is a martingale. This one. And
yeah, is it related to this integral 0 to t of f of t dbt, because that itself is a continuous martingale?
What do you mean? Can
I
you
mean,
say again?
this integral without the square, it's a martingale, right?
No, it's a sub-martingale. Integral without square is a martingale, yes.
Yeah, it's a continuous martingale. So
Yes.
I'm saying, is that martingale somehow related to this sub-martingale minus quadratic variation?
That would depend on f. That would depend on f.
Right.
What
okay.
the exact formula that will come in, that will depend on f.
Right.
That's
okay.
It. But in general, this is the form. So we square it and we just subtract the quadratic variation of this inner process. Is it okay?
Yeah, it's okay with me.
Okay. And in particular, we have expectation of this 0 to t of r dvr minus 0 to s of r dvr whole square given the sigma algebra fs. This is equal to expectation of integral from s to t of f of r dvr, f of r square dt. So this is by the this is actually by the martingale property that since I mean the expected this conditional expectation of the square of the square of a martingale is just the um, I mean we just have to take the we just have to consider the a process the increasing process. So I'll prove this and if we take s equals to 0 in this, so we get the
Sorry, I didn't. So how is this in? If you could go a little above, how is this in particular?
yes, I'll come to the proof of this. I'll explain this.
Okay.
Um, we have this is here. So if s is equal to 0, then we again have this ethos isometric. So expectation of 0 to 0 to t of f of r dvr squared. This is equal to expectation of 0 to t of r squared dr. Oh, this is written dbr, right? Doesn't I mean, so what I was saying was that um, we since we are since we have to um, condition since we are looking at this sub-martingale, the difference this is when we are calculating the conditional expectation of the square of a martingale, we usually have to only check for the increasing process because the martingale has constant expectation. So this is sort of a analog to that. So I'll explain this. So um, firstly we have that.
So what happens if I just naively start expanding the square and so on? Does that give me something?
This square.
Yeah. So you get this integral 0 to t whole squared.
Yeah. I
And
mean
then
this actually would follow from martingale. Basic martingale property because so if say xt is a martingale, then we have expectation of xt minus xs squared fs. This is equal to expectation of xt squared plus xs squared minus xt xs fs, um, and this is equal to expectation of xt squared minus xs squared fs, right? Because uh, this
right,
one,
right.
yeah,
Yes.
um, and and let's see. So now what we can do is we can just uh, xt squared we can just subtract off the quadratic variations basically. Xt minus x squared minus x s plus xt minus xs even if this, right? We can just write this, right? And I've just added and
Uh,
subtracted the quadratic
yes,
variations.
yes.
Yes, so now these things is a this thing and these things are
No.
martingales.
Right.
This thing is a martingale, right? Xt squared minus
Yeah.
quadratic
Yeah.
variation xt. So this term and this term cancels. I mean, when we
Right.
take conditional expectation.
Yes.
So this is equal to xt minus xs given x. So basically this is what I have written here. We have so the quadratic variation of this one is integral of 0 to t of fr squared dr,
Right, right, right.
and
Yeah.
yeah, so this is just by doing
Okay, okay,
this.
okay.
So okay, I'll just write that apply this to 3. Oh. um, so so firstly linearity is clear, right? By linearity of L2, the L2 space, linearity of f maps to this integral is clear.
Yeah, that is by definition, right? Because you can.
Yeah, exactly. So what? Uh, so to prove, so to prove two, to prove two, what we basically have to show is that this we have Fn.
Can you go to the point two?
Yeah,
So I think we showed this for simple. It's showing this for simple
we
processes.
saw.
Yeah.
Yeah, we showed this for simple processes. Now we have to show this so that this works for the closure of simple processes as well. So that requires a small argument. Um,
Okay. Okay.
so it works for fn's. If fn's approximate f, it works for fn's. So we need to show that it works for the limit as well. So fn minus f, we have this one. So proof of 2. Fn minus f L2 of lambda t productivity t equals to 0. So what we need to show that this L2 limit, this preserves these martingale properties. So we have for each fixed n this integral um, fn of s dds this squared minus this fn. Okay, I'll just write the quantity. And so it will be fn 18. Notations are becoming conversant. Yeah. So this is a martingale for each fixed n, and this can be written as 0 to t fns pds squared minus 0 to t fns squared ds. So we need to show that for by the L2 convergence, we have L1 convergence of this martingale to this f dds minus 0 to t f squared ds. So we need to show that this convergence takes place in L1. So since L1 convergence would preserve the martingale property, we will then have that uh, this process will also be a martingale for f basically. So and since L1 is complete, we just need to show that this FNS, this will be Cauchy in the L1 now. So you can write this 0 to t Fn this minus 0 to t Fn is dds. You can write this as minus squared minus ns squared ds, and now just a plus b whole squared formula. uh, by a plus b whole square formula, we can write this as fns plus fns into fns minus ffs into this. And
Uh, can't we simply say that FNs are themselves a Cauchy sequence in L2?
yeah, I mean that is the one which requires a argument. I mean, to move from the Cauchy of L2 of lambda t comma p to move to the Cauchy of this quadratic variation, cosinus in
So
L1 of this quadratic variation, that requires this Cauchy
I
square
see.
inequality.
Okay, okay.
That's why I'm writing this. Otherwise, this is actually not very uh, important even, because it's. I mean, we expect that this should occur. Otherwise, what's the point even defining? Uh, this is just quasi-source inequality. The square.
And the first term is bounded, right?
Yeah, and the first term is bounded, so this
Second
one is
term can be.
bounded by some. You can
Yeah.
write it as c times, let's say,
Okay, okay.
minus f. Yes, and now we can take the expectation basically. Now we can take the expectation.
No, I mean, for the
And
quadratic, this is a deterministic thing, right? Or
no,
not?
no, no, omega.
Yeah,
There is omega.
right, right.
So this is for each fixed, almost surely for all omega this holds true. And we now need to take expectation outside,
And then you apply
expectation of
Cauchy-Schwarz.
non, and then here we need to apply Jensen's
Or
inequality
even
of the.
Cauchy-Schwarz would be.
Uh, so expectation of square root we have.
Is
We
is
need
less
to
than or equal
in
to the is less than or
square
equal
root
to
of
the
expectation.
yeah.
We need to go to square root of expectation.
Uh,
So
yeah,
basically,
I'm saying expectation of square root. So even Jensen or Cauchy-Schwarz would give you the same thing, right?
so I am trying to say this basically. Mod x is
Yeah, isn't this just Cauchy-Schwarz?
uh,
So sorry.
yeah. Just one.
Yeah,
This root x dot one.
yeah. So the
Yeah,
mean is so so basically the variance is positive. That's the same way you say the variance is
yeah.
positive.
And yes. So we
Okay,
are just
okay,
writing this square root of x equals to the square root of x times just one.
yeah, yeah.
Then we are applying causes. Yeah.
Okay.
Yeah. By causes squares we can even do that. Yes. And so by taking expectations, we have that this inner thing is now so by taking expectations, we have the this L1 non is lesser than c times the root of not even the root, we directly have this c times L2 and this is L2 of that lambda t product. So this is the argument basically. So we now
So
have
yeah,
three constraints.
the quadratic for the quadratic variation this is fine, but is the other term also easy?
Other term,
You have to
what
I
was
mean you have to show that the other two integrals also converge in L1, right?
uh,
I mean there was
the
this square thing,
ha
the
ha ha
submartingale.
yeah.
So
So
so that will also go. the same way, right? I mean,
Yeah, basically we have that this 0 to TFS BBS was the L2 limit of this FNS BBS. So since we have a convergence in L2 of this to this, we have convergence in L1 of the square, right? 0 to TFS. Is that okay?
this is just the expectation, right? The expectation of the difference of the square
Yeah,
goes to
yeah,
zero.
yeah. L1,
Right,
L1.
okay.
These
Right, right,
these are all random variables. For fixed
right,
key, these are all random variables. Yes.
right.
So we have that this sequence. This sequence is a Cauchy in L1, and
Yeah,
that is enough to preserve the martingale property.
right, right. Because
So
it's a
hence,
complete space, so whatever you have is
yes, yes,
you have some
yes.
limit and
Not even that. I mean, for martingales, if we have a if
okay,
martingale,
okay. So it's a martingale, and if they converge,
the limit is if a martingale converges in L1 to something, then the limit will also be a
yeah,
martingale,
no.
right?
I mean to say that it does converge to something. You need completeness of L1,
Yeah, yeah, yeah.
and
Completeness
that
of L1.
the limiting thing is a martingale because of this martingale convergence theory.
Yes, yes, yes,
Okay,
yes.
sure.
So this
Uh,
proves that this F, uh, this property, that
right, the second one.
the
Yeah, I mean,
quadratic variation of F is also given by this similar thing, 0 to t,
uh,
integral of 0 to t f t square. So we knew that for simple functions, the quadratic variation is this thing.
no, I mean, so if so we do know that integral 0 to t f of t dbt is a martingale. So if you
Yes,
square it, you have a submartingale,
yes.
and you know that
And
the submartingale.
we have now shown that this is the quadratic variation.
Yeah, submartingale minus something is a martingale, so that whatever that
Yes,
thing has to be of quadratic variation. And,
yes. We
yeah,
have now shown that this is exactly the quadratic variation.
quadratic variation. Right, right. Right. So I think
Yes, it's more than
it's about
yeah.
time about today. Yeah, yeah. Thank you very much. Very nice, and and fortunately, I was able to follow almost all of this for the first time. So, uh,
So
uh,
next day maybe next time I do this, maybe I can give some motivation for some heuristics regarding the ethos lemma, or why
yeah.
that thing is occurring. That
Okay. Okay.
like you said that this integral of dt squared, right? We were discussing. I don't know where it went.
Right. Right. So I
Yeah.
mean, giving actual simple processes which would actually uh,
Yeah. Even
approximate it. Yeah.
so we can even give actual, like the actual exact simple process that approximates it. But even then, like so we can even reduce this theory to like the basic high school calculus that we do. Like in high school, we do not really do anything by Riemann integration, right? We
Right.
just
Right.
apply formulas like
Yeah.
by parts and everything.
Yeah.
So here also, the analog of by parts is basically Ito's formula. So by Ito's formula you can by just mental calculation we can just say what
You
is
can actually
integral of
compute the
dt square.
integrals. You can actually compute the
Yeah,
integral without.
we can
No, no,
actually
yeah,
compute. Yeah,
right. So yeah, the reason I wanted to do the simple processes is sometimes it just gives you a hands-on feel of.
Yeah, and actually there is a very important theorem. So that theorem would have come. So if you give me just 5 minutes, I will just state that theorem again.
Sure.
So um, so this gives you an actual way to evaluating. I'll just turn this evaluating this. Okay, so stochastic integrals. So let f belongs to this space L2 of lambda t comma p, and this is that progressive measurable. We can assume everything, or even we can assume continuous for simplicity. So, so yeah, the assumption comes here, such that we have limit um, limit s converging to p, and s we will choose from 0 to p. Okay. And expectation of fs dot minus fe dot squared equals to 0. So this this property is actually what is known as uh, mean squared continuity. So basically, this is continuous in the L2 sense. So expectation of the limit in case of continuity, we just say this limit exists or this non converges to 0. But we want to say something something stronger and weaker in the same situation, because L2 does not imply almost sure, and almost sure does not imply L2 anyways. But this is what we mean by mean square continuity. And if this holds, then we can write f of t dbt. This is equal to the limit of non-pi tending to 0, and this limit will be in L2 sense, limit of j equals to 1 to n f of sj minus 1 bsj minus bsj minus 1. So this is basically the L2 limit of the Riemann integral. So this is the main point that I wanted to make. So this holds for all f which satisfy this mean square continuity property. So this thing.
So right. So this is some sort of precursor to Ito's thing, or
this so Ito's thing is even more stronger,
right.
not even stronger. I mean just Ito's thing gives you the biparts form to how to get functionals. I mean, like you said, bt squared, and so
Yes. So
functions
I'm
of
saying,
this.
suppose if I have some f which satisfies this mean square continuity, then I can
Yes.
actually use this, because
Then we can do the Riemann integral thing.
yeah, you can
Omega by
actually
omega.
compute the Riemann integrals and then take limit. So
Then take the L2 limit. So this
so
is this.
you have some sort
Yeah.
of, without using this Ito thing, you have actually
We have this.
So that property is satisfied by continuous functions, right?
no, right? Because
Not
almost sure.
only.
Yeah. So
Yeah,
the issue, I
we
think,
have to
almost sure
have this
convergence.
one.
Right.
Yeah, that's why I said it's simultaneously weaker and stronger. I mean, almost sure does not imply L2. And L2 also does not imply almost sure. So,
But so for continuous function, that limit pointwise goes to 0, right?
yeah, I mean, see, so for continuous function, since this interval is finite, we have,
Huh.
and if it's bounded and everything, so if it's uniformly bounded omega by omega, then we have everything. But for Brownian motion, for example, we don't have
Right, right. Yeah, yeah,
boundedness,
yeah, yeah, yeah. Yeah, yes,
but
yes. Okay.
but we do have this L2 mean squared.
Yeah, yeah, okay, yeah.
And even this property is actually very important. I mean, if we have seen that functional martingale convergence theorem or things like that, then this is actually this is actually one of the assumptions, that if that is actually a central, there is a stronger version of the Donskoy's theorem. So this is actually one of the assumptions in that theorem. So this property is, again, as I said, it's simultaneously weaker and stronger. So this gives you a so our known way. So Riemann integral is our comfort zone. So, and in fact, Ito's lemma and Ito's formula will be proved using this. We will need to use this to prove Ito, at least in the way I saw. There might be other proofs. So,
Okay.
So this.
Can you go bit up?
Yes, yes.
So, just below.
This one.
Just
Yes.
no, no, below, below.
Yes.
So this is this L2 limit that you said.
Yes.
So by definition, that is that M2C limit, right? That
Yes. Yeah. Uh,
and that implies L2 convergence of this, right? That's the
yeah. So L2 of lambda t product with P of norm of Fn minus F convergence implies the L2 in the probability sense convergence of this particular random variables. So this is
I see.
just
But
convergence of
martingale
random.
wise, I see.
So
But if I
this
see
works
them
for
as a
all
martingale,
T.
then but if
Yeah.
I see them as a martingale, then this is that under that metric that is the convergence, right? As martingale.
Yeah, because if you see them as martingales, then we have this L2 of this endpoint. This, if we replace T by capital T, then that capital T itself will be enough for this entire martingale process. So that was the Dubs result that we saw. Yeah.
Right, okay.
So that's why the endpoint is important. I mean, so we are just, so in that one we just check for this small t or this capital T. If we just check for capital T, that is enough to do that for the entire process. So that's the our heuristic.
Okay. I'll stop the meeting then now.
Okay. Okay.
I'll stop the recording.
Yeah, I'll just